In examples 1 through 6, we were solving systems of linear equations, and our result gave us the unique point where those two lines intersected with one another. When we're solving systems, though, we do have two special cases that we need to consider. The first being the case where we have an inconsistent system, meaning there is no solution to the system. So we want to take a look at what that would look like as we start solving that problem and talk about what we mean by the idea of that inconsistent system, or the idea that there is no solution. So labeling our equations as 1 and 2, we could start off by using the substitution method. We can solve equation 1 for y very easily by just subtracting 2x to the other side. And then we can drop that result in, or substitute that result in, to our second equation. And then distribute through and work on solving this expression, or solving this equation, which is now just in one variable. So this would give us 10x plus 40 minus 10x is equal to 13. 10x minus 10x would cancel out to 0, so we would end up with 40 is equal to 13, which is clearly not true. So since we ended up with a false statement after our variables canceled out completely, that means there's no solution, or what we refer to as an inconsistent system. So there is no pair of points, or coordinate pair, x, y, that we could substitute into these two equations that would make them both true. So let's go ahead and refer to this as method 1 for identifying this inconsistent system, and consider a second method for trying to achieve that same result. This time around, what we're going to do is take both equations and solve them for y. So we already have the first equation solved as y equals 8 minus 2x. We could take equation 2 and subtract 10x to the other side, and then divide both sides by 5. To get y equals 13/5 minus 2x. If we take one more step, just rearranging the order of the terms on the right-hand side, we could rewrite this as y equals negative 2x plus 8, and y equals negative 2x plus 13/5. So now what we have are both equations rewritten in y equals mx plus b form, that's slope-intercept form. And if we recall some of the characteristics of slope and intercept and what they mean about our lines, we can see that we have identical slopes. So both of these equations have a slope of negative 2, but we have different y-intercepts. So two lines that have the same slope but different y-intercepts are two parallel lines. So two parallel lines are lines that never intersect with one another, which is why when we worked this out using either of those methods for solving a system of equations, we get a false statement and no solution, because these two lines will never intersect with one another. So we can discover that by using this method for solving systems of equations, either substitution or elimination, or we could identify that by comparing both of our equations in slope-intercept form. Or the other way to think of it might be as using this as a backup method just to verify that this solution, or this statement, which is not a solution, was correct versus perhaps maybe making a small arithmetic error along the way. But again, what really happened here is that our variables canceled out and we were left with a false statement, meaning that this system of equations has no xy coordinate pair that will ever make it true.